Hello students, our next topic is the driving forces of the tides. This is an example for principle of equivalence. So here we know that earth is in free fall towards the sun, okay, and according to the principle of equivalence, since it is an accelerating frame, it should be impossible to observe the sun's gravitational force on an earth-bound system or a system on earth. So it is impossible to observe the sun's gravitational force on earth. However, the equivalence principle only applies to local systems. Okay, now we know that here our example is the driving forces of tides. The tides arises because the sun and the moon produces an apparent gravitational field that varies from point to point on the earth's surface. Due to the gravitational field by the sun and moon produces an apparent gravitational field which is the cause of tides. So although moon's effect is larger than that of sun, we here consider only the sun's gravitational field alone. So we are not taking the gravitational field of moon. Okay. So this is our sun, this is our earth, this is the distance between RS shows the distance from the center of the sun and earth. Okay, this is the direction of acceleration field of the sun at the center of the earth. Okay, so the gravitational field GO, since it is at the center, GO is equal to Gms by Rs square into n cap. Ms is the sun's mass, Rs is the distance between the center of the sun and the center of earth, and n is the unit vector from the earth towards the sun. So this is in this direction the field is applying. So the earth is accelerating towards the sun at this rate. A is equal to GO. So this is the acceleration of earth towards the sun. This is the so our earth is a frame which is a non-inertial frame and has an acceleration GO, right? So if GR is the gravitational field of the sun at some point R on earth, so we have defined the gravitational field at the center, and GR is the gravitational field of the sun at some point R on the earth, where the origin of R is at the center of earth. Then the force on mass M, so the force on mass M at R is F is equal to mgr. Okay, so if we are an observer on the earth, the apparent forces, we know that we should include the fictitious force, right? Since this is a non-inertial frame or an accelerating frame. So the apparent force we observe, so the observer is on the earth, F dash is equal to F minus ma. So what is F? F is the force by the sun on a mass m at a distance r. So it is mg of r minus mgo. So this is an r dependent factor. So at various points this value will be changing. So the apparent force will be changing with respect to r. So the apparent field G dash is equal to F dash by m, that is equal to, from this equation you get G of r minus GO. Now this is our figure of earth. We take 4 points A, B, C, D. These are the 4 different points on which G is different due to the distance from the earth. Okay, these are the 4 points we are considering, and we are trying to find out what are the differences or the apparent gravitational acceleration at all these points. Okay, so G of r at different points. So at this point, this is the direction of GA. This GA will be greater than GO since the distance is shorter. So the vectors here, the drawn vectors here represents actually the magnitude of the value. Okay, so GA is greater than GO and GC is less than GO since the distance is longer. Okay, now the magnitudes of GB and GD, this is GB and GD, are approximately same. Okay, but they are not parallel and there is an angle difference between them. So this is the sketch. Okay, now we are going to find out what are the values of the field at A, B, C, D points. The parent field G dash at all these points. It is given by the relation G minus GO. Okay, so first we take the points A and C, the equivalent opposite points. So we find out G dash A, the parent the gravitational field at the point A. Okay, since the distance is Rs minus Re, which is the radius of Earth, Ga will be equal to Gms minus by Rs minus Re square. So Rs is replaced by Rs minus Re square. And we know that Ga and Go are parallel, okay, along the same direction. So the magnitude of the apparent field at A. So we are going to find out the magnitude of apparent field at A is G dash A is equal to Ga minus Go. So what is Ga? Field at A, it is Gms minus by Rs minus Re whole square minus Gms by Rs square. We take Gms by Rs square outside, and inside the bracket it will be 1 by this term. Okay, so this term is very much less than 1, so you can take it on the numerator, and you can expand in the terms of 1 minus x raised to minus n. Okay, then you get 1 minus 2 Re by Rs, and the higher order terms are neglected. Okay, so you get the relation. It is approximately 2 Go Re by Rs. The value of Re by Rs is much less than 1. Okay, now similarly, so you got the value of G dash A at the point A. It is equal to 2 Go Re by Rs. Similarly, at the point C, where the distance is Rs plus Re, you get the same value with a negative sign. So we obtain G dash C at an equivalent opposite point G dash C. You get it as minus 2G0 Re by Rs. These two are radially opposite points. So our figure is like this. You get G dash A in this direction with this much magnitude, and G dash C with this much magnitude. Both are equal and opposite. So there is a outward pull or outward gravitational acceleration experienced at these points. Now what about B and D? So in order to find out B in the acceleration at points B and D, we take the approximation, the same distance. It is actually the same distance from to the sun. We take the small angle which is equal to alpha. Okay, now GB is not parallel to GA, and angle between them alpha is approximately equal to Re by Rs. Okay, that is equal to 4.3 into 10 raised to minus 5, which is much less than 1. So to this approximation, this is the direction of GB and this is the direction of GO. So we reconstruct this triangle GB and GO, and this angle is actually alpha itself. So you can relate these three terms. How can you relate GB, GO and G dash B? You get alpha is equal to or tan alpha. You take tan alpha is equal to G dash B by GO, or G dash B is equal to GO alpha. So alpha here it is Re by Rs. So it is GO Re by Rs. Okay. So at this point, the value of apparent field is equal to GO Re by Rs. By symmetry, G dash D is equivalent opposite to G dash B. That will be equal to minus GO Re by Rs. Okay. So the direction of G dash B is in this direction and G dash D is in this direction. Okay, so you got all the 4 values as well as the directions of the fields at the 4 points. Now in this figure you can see that this is the direction of field at A and this is the direction of field at C. Here we are drawing only the starting points. Here it is towards the center and here too it is towards the center. So the sketch show at various G dash R at various points. The diagram is the starting points only. Okay. And now the forces at A and C. What is the function of the forces at A and C? They tend to lift the ocean. So at these two regions, the ocean get lifted, and the forces at B and D tend to depress them. At these 2 points, the ocean get depressed. Okay, at these 2 points it gets lifted, and at these 2 points it gets depressed. If the earth were uniformly covered with water, the tangential force components would cause the 2 tidal bulges to sweep around the globe as the earth rotates. But actual picture is much complicated than this. This picture explains the twice daily ebb and flood of the tides, but the actual motion depends on in a complicated way on the response of the ocean as the earth rotates and on the local topography. Okay, this is how the tides get lifted and depressed. So here you can see a figure from the internet, high tides and low tides figure. Okay, thank you.